Welcome to probably the most challenging section in this course, but also one of the most exciting ones and most rewarding ones. So up until this point, we have only focused on how React concepts and features work in practice. But now it's time to understand how things actually work internally inside React behind the scenes. So just like my other courses, this course also includes a really deep dive, which most students absolutely love. Because this information you're about to learn will not only make you a much better and more confident React developer, but it will also allow you to ace the most common React interview questions with all the confidence that you need in order to nail that job. And I would go as far as saying that this knowledge will actually put you right in the top 5% of all React developers. Now, again, this section is quite intense, and it should probably be in the advanced part of the course. But since there is so much important stuff that we need to talk about before moving on, I decided to place it right here. If at some point it becomes a bit too much, or if you become bored, please watch at least the final lecture of the section, where I'm briefly gonna summarize everything we covered. So that video really is a must watch. But anyway, without further ado, let's dive right in and uncover how React works. Now, before we go learn about how React works behind the scenes, let's quickly set up and walk through a small demo project that we're gonna need in a few lectures of this section. Now, this time around, we will do things a bit differently. So we will not create a new project using create React app. Instead, in the starter files, I already basically have that entire project for you to copy. So open up the starter files, and then here in this folder called How React Works, let's copy this entire starter folder. So copy all of this right into the folder where we are building our projects. And so then simply call it How React Works. So you see that here we actually have the source folder, we have the public folder, and also these other files that are always automatically created by create React app. But again, this time we are not doing that because, well, everything has been done already for us. And so now all we have to do is to take this folder, open it up in VS Code like this, and then we need to install all the packages. So the node modules folder, which is the folder where all the npm packages are installed, is of course not here. So all the libraries like React, React DOM, and so on, they are not here. So we need to install them. But that's fortunately very easy. So let's open up our terminal here. It's here in view. And well, that's really small here. And as always, make sure that you are in the correct folder. And then all we have to do is to say npm install or npm I for short. So hit enter, and then this will install all the packages that are necessary for this create React application. So it will get this information here from this package.json file. Okay, and we see that it's already done. And so we can now start this project. So just write npm start. And then in my case here, it's asking me if I want to run the app on another port. And so that's because I already had something running here on 3000. So that's basically the demo project, but let's close that for now actually. So just inspecting this, and then let's open up our app.js file as always. So this time around in this section, I gave you this already started project so that you can now get the experience of looking at a project where someone already started writing some code. So that's exactly what we have here. So some code here has already been written, and so you cannot pretend that basically some other developer on your team wrote this. So it's extremely important that you be able to understand other developers' code, especially when you work on a team as a professional React developer someday. And so, before we now start this section, I just want us to quickly walk through this code here so I can explain you how it works on a high level. And then by doing so, you can see how we can effectively read code that we didn't write ourselves. So let's start in the app component here. And all that one does is to include the tabbed component. And it passes the content in there, which is simply this array of objects here. So pretty standard. Then the tabbed component has some state variable here, which indicates the current tab. So it seems like this is a number. And then down here, we can see that the active tab state is used to render this tab content component using as the content array at the position of the currently active tab. So this at here is basically modern JavaScript, which is the same as this here. So basically reading something out of an array. And that array, again, is this content array up here. So for example, if the state here was 2, then the content here in the tab would be 0, 1, 2. So it would be this object right here. All right, let's just put this back here to this more modern form. And then let's check out what this tab content here actually is. And it's also always a good idea to take a look at the component tree. And so let's make this here bigger. And so indeed we have the app, we have tabbed, and then we have the tab content in there. And of course we also have these 4 tabs, but we will leave them for a bit later. So in here, in the tab content, let's see what we have. So we get the tab item, which is basically the content that we're going to use here. So we can double click on that, and then we see where it has been used. So we see that we use item.summary and item.details. Then we also see that we have 2 state variables here. So that's show details and set show details. And again, by double clicking, VS Code will then highlight all of them. So here we can see that we're doing some conditional rendering with this show details. And so, yeah, by default, this is true. And then only in that case, we are displaying the item details. And then we change that state down here where we have set show details in this button. And so this here is exactly that button. So if we click that, then here the text disappears. So this paragraph right here disappears. Right? Then we also have these 2 buttons down here, but we see that they have no event handler attached. So if we click here, then nothing happens. Then finally, we also have those hearts here, and that's why we have this second state of likes. So you see that likes is indeed used here, and then this button here has the handle ink function. So this first one here, while the second button again has no handler. So here nothing happens, but here each time we click, basically 1 like is added there. And so that's because of the handle ink function. So what this one does is simply take the current likes and adding 1 and then setting that as the new likes state. Now notice how here we didn't use a callback function in order to set state based on the current state, but more about that later. So I think this component here is pretty clear. And so let's now go back here and see what these tabs here actually are. So here we have these 4 tabs, and notice how we are actually writing them one by one manually and not looping over some array. So our array has these 3 elements here. And so the first 3 elements, so these 3 are for those 3 objects. And then we have another one where the number is 3. but let's take a look at that a bit later. So here we have the num as a prop, we have the active tab, and we have the onClick prop. And as the onClick, we are simply passing the setActiveTab stateSetter function. Now let's go here into the tab and see what happens there. So basically a tab is just a button. So it's these buttons right here. And what happens when we click on this button is that the onClick function is called with the current number. So let's then actually go back to where these props are passed so that we can understand what the onClick and the num actually are. So onClick is setActiveTab, and num are these numbers here. And so basically when we click on this first tab, it means that the active tab will get set to 0. And the same down here. So when we click on this tab right here, then the active tab will get set to 1, which is exactly what we have here. Then, based on this state, as I explained in the beginning, we see that the tab content will be rendered, at least if that value is less or equal to. So if it's greater than 2, which happens in this case, then the different content will be displayed. So let's check that out. And so this one is simply this one div, which has a simple h4. Okay, so again, basically the goal of this other tab right here is just to display this different content component right here. So let's see that in action. And so, indeed, when we click on tab 2, you see that the content here changed. And so the title here and the text are exactly what we have here in this second object. And then the same here. So here we now have the third object. So the title and the text. And finally, the last one is for that different content. And you saw that down here, actually the component tree changed. All right. And here, if we wrote any other number, like 0, then of course, you see that the number changed here. So that is always the number plus 1, and we get then the very first object. So now it says React is a library for building UIs. So just like here. And also both of them are now marked active, which also happens inside that tab component. But of course, let's put it back to 2. And with this, I think it is pretty clear what this very small demo application does. But before you move on to the next lecture, make sure that you take some more time to analyze this code on your own so that you truly understand what exactly is happening here. Let's start this section with the conceptual difference between React components, component instances, and React elements. Knowing about this difference will hopefully make it a bit more clear what actually happens with your components as you use them. And also, this is a pretty common interview question, and so this topic is definitely worth learning about. And let's begin by taking another look at components. So, components are what we write in order to describe a piece of the user interface. And a component is just a regular JavaScript function, but it's a function that returns React elements. So it returns an element tree. And we usually write these elements using the JSX syntax. Now, a component is a generic description of the UI. So we can essentially think of a component as a blueprint or a template. And it's out of this one blueprint or template that React then creates one or multiple component instances. Now, React does this each time that we use the component somewhere in our code. For example, the tab component that we saw in the last slide is used, so it is included 3 times in this app component. And so, therefore, 3 instances of tab are placed in a component tree, so in our actual application. Behind the scenes, this happens because React will call the tab function 3 times, so 1 time for each instance. So we can say that an instance is like the actual physical manifestation of a component living in our component tree, while the component itself is really just a function that we wrote before being called. And actually, it's each instance that holds its own state and props, and that also has its own life cycle. So basically, a component instance can be born, it can live for some time, until it will eventually die. So it's a bit like a living organism, really. Now, in practice, we many times just use the terms component and component instance interchangeably. For example, we just say component lifecycle and not component instance lifecycle. And we also say that a UI is made up of components, not of component instances, even though instances would technically be more accurate. Okay, so just keep that in mind in the future when you read documentation or some Stack Overflow post or something like that. But anyway, as React executes the code in each of these instances, each of them will return one or more React elements. So, as we learned when we first talked about JSX, behind the scenes, JSX will actually get converted to multiple React.createElement function calls. Then, as React calls these createElement functions, the result will be a React element. So, a React element is basically the result of using a component in our code. It's simply a big, immutable JavaScript object that React keeps in memory. And we will take a look at this later in our code. But what is this object actually? Well, a React element basically contains all the information that is necessary in order to create DOM elements for the current component instance. And so, it's this React element that will eventually be converted to actual DOM elements and then painted onto the screen by the browser. So, based on all this, the DOM elements are the actual, final, and visual representation of the component's instance in the browser. And again, it's not React elements that are rendered to the DOM. React elements just live inside the React app and have nothing to do with the DOM. They are simply converted to DOM elements when they are painted on the screen in this final step. Okay, so this is the journey from writing a single component to using it multiple times in our code as a blueprint, all the way until it's converted to a React element and then rendered as HTML elements into the DOM. So I hope you found this interesting and useful, and if you did, then let's move on to the next video and take a look at all this in code. So as promised, let's now shortly look at component instances and React elements in our code. So what I want to do in this lecture is just a couple of quick experiments to show you some interesting things. So first off, we can actually look at a component instance simply by using the component and logging it to the console. So let's try that out. So actually right out here, we can write JSX like this. So let's use the different component or the different content component because this one doesn't have any state. All right, and if we run this, then we should see something in the console. And indeed, there it is. So as soon as React sees this right here, it will internally call the different content function and will then return this React element. So just like we learned in the previous video. So let's take a quick look at this. And while this is not really interesting, we can see that the type here is of different content. And so that's exactly the name of the component right here. We can also see that we didn't pass in any props, but which we actually could. So let's just do test equals 23. And so then we should see that right here. So now in the second one. And indeed, there it is. So again, this is what React internally use to then later create our DOM elements. Now, if you're wondering what this weird $$ type of thing here is, well, this is simply a security feature that React has implemented in order to protect us against cross-site scripting attacks. So notice how this is a symbol, and symbols are one of the JavaScript primitives which cannot be transmitted via JSON. Or in other words, this means that a symbol like this cannot come from an API call. So if some hacker would try to send us a fake React element from that API, then React would not see this type of as a symbol. Again, because symbols cannot be transmitted via JSON. And so then React would not include that fake React element into the DOM. So protecting us against that kind of attack. All right. But anyway, let's come back here and try something else. So if React calls our component internally when it renders them, so just as it did here in this previous line, then maybe you have wondered, why don't we just call components directly? So why should we write it like this when we could also write different content like this? So basically calling the function ourselves. Well, there is really nothing stopping us from doing so. So if we save this, then we actually get a result as well. Let's just reload here so that we only get these two outputs. So one output from here and one from here. So you see that even here in this case, we still got a React element like this. However, it is a very different one. So this one no longer has the type of different content, and instead it is a div, which is basically just the content of that component. So this div here is now the type of this React element. And we can also see that because the props include the class name of tab content. So what this means is that right now React does no longer see this as a component instance, and instead it just sees the raw React element, which is really not what we want. So when we write, or actually when we use a component, we want React to see the component instance and not the raw output element like this one. So never do this, what we did right here. And let's actually demonstrate this one more time, but now inside the component here. So after all this, let's enter JavaScript mode here, and then let's just call, or actually tab content. This time let's call tab content, and we can pass in props just like this. So we pass in an object, and then item, and then let's say content at 0. And, well, we got some errors here, but let's try to reload. And now this somehow works. So you see that actually we got a second tab content rendered down here. So it looks like this works, right? Well, not so fast. Let's check out our component tree here again. We need some more space. And so now you see that we still only have one tab content here in our component tree. And so this happened exactly because of what I explained before, which is that when we call a component directly like this, then React no longer sees it as a component instance. Now we can also see that the state that this component manages is actually now inside the parent state, or the parent component. So if we check out the tabbed component here, you see that it has the normal state that it had before, which is this active tab, but it also has some other hooks here, which come from tab content. So these two are the two hooks that are inside this component, but they don't really belong here. So we actually want them to be inside tab content and not inside, well, not here inside the tabbed component. So what this means, again, is that this is here not really a component because it cannot even manage its own state at this point. So for all these reasons, you should never ever do what we just did here, because this will create multiple problems, such as violating the rules of hooks that we will talk about later. So instead, as you already know, always render it inside the JSX, so just like this. And so here we just use the component, so basically this blueprint, like we have always been doing. And so then React calls the component and actually recognizes this as a component instance. All right. So let's reload here again, and then we are back to normal. All right. And here we can see one of those examples that we talked about in the previous lecture. So we wrote one tab component here. So this is like the blueprint, but then we have 4 component instances, each with its own state and its own props. We are now ready to finally learn about how exactly React renders our applications behind the scenes. Now there's so much to learn here that I split up this lecture into 3 parts. So it's this video and the next 2 ones. This one serves more as an overview, and then in the next 2 videos we're gonna go really deep into some React internals. And let's start with just a small recap, so that we're all on the same page. So as we build our applications, what we're really doing is building a bunch of components. We then use these components inside other components as many times as we want, which will cause React to create 1 or more component instances of each component. So these are basically the actual physical components that live in our application and hold state and props. Now, as React calls each component instance, each JSX will produce a bunch of react.createElement function calls, which in turn will produce a React element for each component instance. And so this React element will ultimately be transformed to DOM elements and displayed as a user interface on the screen. So we have a pretty good understanding of the initial part of this process, so of transforming components to React elements. However, what we don't understand yet is the second part of the process, so how these React elements actually end up in the DOM and displayed on the screen. Well, luckily for us, that is exactly what this series of lectures is all about. So, in this lecture, we're going to have a quick overview of each of the phases involved in displaying our components onto the screen. Then we're going to zoom into each of these phases to learn how the entire process works internally behind the scenes. So, this process that we're about to study is started by React each time that a new render is triggered, most of the time by updating state somewhere in the application. So state changes trigger renders, and so it makes sense that the next phase is the render phase. In this phase, React calls our component functions and figures out how it should update the DOM, so in order to reflect the latest state changes. However, it does actually not update the DOM in this phase, and so React's definition of render is very different from what we usually think of as a render, which can be quite confusing. So again, in React, rendering is not about updating the DOM or displaying elements on the screen. Rendering only happens internally inside of React, and so it does not produce any visual changes. Now, in all the previous sections, I have always used the term rendering with the meaning of displaying elements on the screen, because that was just easy to understand and it just made sense, right? However, as we just learned, the rendering that I used to mean is really this render plus the next phase. And speaking of that next phase, once React knows how to update the DOM, it does so in the commit phase. So in this phase, new elements might be placed in the DOM, and already existing elements might get updated or deleted in order to correctly reflect the current state of the application. So it's really this commit phase that is responsible for what we traditionally call rendering, not the render phase. Okay? Then finally, the browser will notice that the DOM has been updated, and so it repaints the screen. Now this has nothing to do with React anymore, but it's still worth mentioning that it's this final step that actually produces the visual change that users see on their screens. Alright, so let's now zoom into each of these different steps, starting with the triggering of a render. So there are only two ways in which a render can be triggered. The first one is the very first time the application runs, which is what we call the initial render. And the second one is a state update happening in one or more component instances somewhere in the application, which is what we call a re-render. And it's important to note that the render process really is triggered for the entire application, not just for one single component. Now, that doesn't mean that the entire DOM is updated, because remember, in React, rendering is only about calling the component functions and figuring out what needs to change in the DOM later. Now, again, this might seem confusing now, because earlier in the course, I made it seem as though React only re-renders the component where the state update happened. But that's because we were learning how React works in practice. And in fact, when we look at what happens in practice, it looks as if only the updated component is re-rendered. But now we are learning how React actually works behind the scenes. And so now we know that React looks at the entire tree whenever a render happens. Finally, I just want to mention that a render is actually not triggered immediately after a state update happens. Instead, it's scheduled for when the JavaScript engine basically has some free time on its hands. But this difference is usually just a few milliseconds that we won't notice. There are also some situations, like multiple set state calls in the same function, where renders will be batched, as we will explore a bit later. So, this is how renders are triggered, which is the easy part. What follows is the hard part, which is the actual rendering. And so let's learn all about that in the next video. Welcome back to probably the most complicated and most confusing lecture of the entire course. But I don't say this to scare you, because this might also be the most interesting and fascinating lecture of the course. Now, if you don't immediately understand 100% of what I'm going to teach you here, that's absolutely fine. So don't stress about it at all. Again, you can use React without knowing any of this stuff. But if you have a curious mind and feel the need to understand how React does what it does, then this video is for you. Now, before we even start, let's first go back to where we first learned about the mechanics of state. Remember this diagram? Well, back then, I told you that we can conceptually imagine this as a new view being rendered on the screen, so into the DOM. However, now we know that this was technically not true, because rendering is not about the screen or the DOM or the view. It's just about calling component functions. I also told you that whenever there is a re-render, React discards the old component view and replaces it with a brand new one. However, that's also technically not true. So the DOM will actually not be updated for the entire component instance. So if those things are not true, then let's now learn what happens instead and how rendering actually works. So, in the previous lecture, we talked about how renders are triggered. In this lecture, we're going to learn all about how renders are actually performed in the render phase. So, at the beginning of the render phase, React will go through the entire component tree, take all the component instances that triggered a re-render, and actually render them, which simply means to call the corresponding component functions that we have written in our code. This will create updated React elements, which all together make up the so-called virtual DOM. And this is a term that you might have heard before, and so let's dig a little bit deeper now into what the virtual DOM actually is. So on the initial render, React will take the entire component tree and transform it into one big React element, which will basically be a React element tree like this one. And this is what we call the virtual DOM. So the virtual DOM is just a tree of all React elements created from all instances in the component tree. And it's relatively cheap and fast to create a tree like this, even if we need many iterations of it, because in the end, it's just a JavaScript object. Now, virtual DOM is probably the most hyped and most used term when people describe what React is and how it works. But if we think about it, if the virtual DOM is just this simple object, it's actually not such a big deal, right? And that's why the React team has really downplayed the meaning of this name, and the official documentation actually no longer mentioned the term virtual DOM anywhere. But I'm still using this term here because everyone still uses it, and also because it just sounds a bit nicer than React element tree. Also, some people confuse the term with the shadow DOM, even though it has nothing to do with the virtual DOM in React. So the shadow DOM is actually just a browser technology that is used in stuff like web components. But anyway, let's now suppose that there is going to be a state update in component D, which will of course trigger a re-render. That means that React will call the function of component D again and place the new React element in a new React element tree, so in a new virtual DOM. But now comes the very important part, which is this. Whenever React renders a component, that render will cause all of its child components to be rendered as well. And that happens no matter if the props that we pass down have changed or not. So, again, if the updated components returns one or more other components, those nested components will be re-rendered as well, all the way down the component tree. This means that if you update the highest component in the component tree, in this example component A, then the entire application will actually be re-rendered. Now this may sound crazy, but React uses this strategy because it doesn't know beforehand whether an update in a component will affect the child components or not. And so by default, React prefers to play it safe and just render everything. Also, keep in mind once again that this does not mean that the entire DOM is updated. It's just the virtual DOM that will be recreated, which is really not a big problem in small or medium-sized applications. Okay, so with this, we now know what this new virtual DOM here means, and so let's keep moving forward. So what happens next is that this new virtual DOM that was created after the state update will get reconciled with the current so-called fiber tree as it exists before the state update. Now this reconciliation is done in React's reconciler, which is called fiber, and that's why we have a fiber tree. Then the result of this reconciliation process is going to be an updated fiber tree, so a tree that will eventually be used to write to the DOM. So this is a high-level overview of the inputs and the outputs of reconciliation. But of course, now we need to understand what reconciliation is and how it works. So you might be wondering, why do we even need stuff like the virtual DOM, a reconciler, and those fiber trees? Why not simply update the entire DOM whenever state changes somewhere in the app? Well, the answer is simple. Remember how we said that creating the virtual DOM, so the React element tree for the entire app, is cheap and fast because it's just a JavaScript object? Well, writing to the DOM is not cheap and fast. It would be extremely inefficient and wasteful to always write the entire virtual DOM to the actual DOM each time that a render was triggered. Also, usually when the state changes somewhere in the app, only a small portion of the DOM needs to be updated, and the rest of the DOM that is already present can be reused. Now, of course, on the initial render, there is no way around creating the entire DOM from scratch. But from there on, doing so doesn't make sense anymore. So imagine that you have a complex app like udemy.com. And when you click on some button there, then show modal is set to true, which in turn will then trigger a modal to be shown. So in this situation, only the DOM elements for that modal need to be inserted into the DOM, and the rest of the DOM should just stay the same. And so that's what React tries to do. Whenever a render is triggered, React will try to be as efficient as possible by reusing as much of the existing DOM tree as possible. But that leads us to the next question. So, how does React actually do that? How does it know what changed from one render to the next one? Well, that's where a process called reconciliation comes into play. So reconciliation is basically deciding exactly which DOM elements need to be inserted, deleted, or updated in order to reflect the latest state changes. So the result of the reconciliation process is going to be a list of DOM operations that are necessary to update the current DOM with the new state. Now, reconciliation is processed by a reconciler, and we can say that the reconciler really is the engine of React. It's like the heart of React. So it's this reconciler that allows us to never touch the DOM directly, and instead simply tell React what the next snapshot of the UI should look like based on state. And as I mentioned before, the current reconciler in React is called Fiber. And this is how it works. So during the initial render of the application, Fiber takes the entire React element tree, so the virtual DOM, and based on it, builds yet another tree, which is the Fiber tree. The Fiber tree is a special internal tree where for each component instance and DOM element in the app, there is one so-called fiber. Now, what's special about this tree is that unlike React elements in the virtual DOM, fibers are not recreated on every render. So the fiber tree is never destroyed. Instead, it's a mutable data structure, and once it has been created during the initial render, it's simply mutated over and over again in future reconciliation steps. And this makes fibers the perfect place for keeping track of things like the current component state, props, side effects, list of used hooks, and more. So the actual state and props of any component instance that we see on the screen are internally stored inside the corresponding fiber in the fiber tree. Now, each fiber also contains a queue of work to do, like updating state, updating refs, running registered side effects, performing DOM updates, and so on. This is why a fiber is also defined as a unit of work. Now, if we take a quick look at the fiber tree, we will see that the fibers are arranged in a different way than the elements in the React element tree. So instead of a normal parent-child relationship, each first child has a link to its parent, and all the other children then have a link to their previous sibling. And this kind of structure is called a linked list, and it makes it easier for React to process the work that is associated with each fiber. We also see that both trees include not only React elements or components, but also regular DOM elements, such as the H3 and button elements in this example. So both trees really are a complete representation of the entire DOM structure, not just of React components. Now, going back to the idea that fibers are units of work, one extremely important characteristic of the fiber reconciler is that work can be performed asynchronously. This means that the rendering process, which is what the reconciler does, can be split into chunks, some tasks can be prioritized over others, and work can be paused, reused, or thrown away if not valid anymore. Just keep in mind that all this happens automatically behind the scenes. It's completely invisible to us developers. There are, however, also some practical uses of this asynchronous rendering, because it enables modern so-called concurrent features like suspense or transitions starting in React 18. It also allows the rendering process to pause and resume later so that it won't block the browser's JavaScript engine with too long renders, which can be problematic for performance in large applications. And again, this is only possible because the render phase does not produce any visible output to the DOM yet. Okay, so at this point we know what the fiber reconciler is and how the fiber tree works. But now it's time to talk about what fiber actually does, which is the reconciliation process. And the best way to explain how reconciliation works is by using a practical example. So let's take the virtual DOM and the corresponding fiber tree from the last slide, which correspond to this piece of code right here. So in the app component, there is a piece of state called showModal, which is currently set to true. And you can pause the video here to analyze it, but it's not really necessary. So let's say now that the state is updated to false. This will then trigger a re-render, which will create a new virtual DOM. And in this tree, the modal and all its children are actually gone, because they are no longer displayed when showModal is not true. Also, all remaining React elements are yellow, meaning that all of them were re-rendered. And do you remember why that is? That's right, it's because all children of a re-rendered element are re-rendered as well, as we just learned a few minutes ago. But anyway, this new virtual DOM now needs to be reconciled with the current fiber tree, which will then result in this updated tree, which internally is called the work in progress tree. So whenever reconciliation needs to happen, Fiber walks through the entire tree step by step and analyzes exactly what needs to change between the current fiber tree and the updated fiber tree, based on the new virtual DOM. And this process of comparing elements step by step based on their position in the tree is called diffing. And we will explore exactly how diffing works a bit later in the section, because that's actually pretty important in practice. But anyway, let's quickly analyze our updated fiber tree, where I marked new work that is related to DOM mutations. So first, the btn component has some new text, and so the work that will need to be done in this fiber is a DOM update. So in this case, swapping text from height to rate. Then we have the modal, overlay, H3, and button. So these were in the current fiber tree, but are no longer in the virtual DOM, and therefore they are marked as DOM deletions. Finally, we have the interesting case of the video component. So this component was re-rendered because it's a child of the app component, but it actually didn't change. And so as a result of reconciliation, the DOM will not be updated in this case. Now, once this process is over, all these DOM mutations will be placed into a list called the list of effects, which will be used in the next phase, so in the commit phase, to actually mutate the DOM. Now, what I showed you here was actually still a bit oversimplified, if you can believe that. But I think that this is more than enough for you to understand how this process works. Okay, so that was quite a deep dive. But now we're back here in the high-level overview of the render phase. So we learned that the result of the reconciliation process is a second updated fiber tree, plus basically a list of DOM updates that need to be performed in the next phase. So React still hasn't written anything to the DOM yet, but it has figured out this so-called list of effects. So this is the final result of the render phase, as it includes the DOM operations that will finally be made in the commit phase, which is the topic of our next video. So if you don't want to break the flow, then let's move on there right now. Welcome back to part 3 of how rendering works behind the scenes. So we just finished learning about the render phase, which resulted in a list of DOM updates. And this list will now get used in the commit phase. Now, technically speaking, the current work in progress fiber tree also goes into this commit phase, but let's keep it simple here. So these are more conceptual diagrams so that we can understand what is happening, not a 100% accurate description of the algorithms inside React. All right. But anyway, as you know by now, the commit phase is where React finally writes to the DOM. So it inserts, deletes, and updates DOM elements. You will sometimes also read that React flushes updates to the DOM in this phase. So basically, React goes through the effects list that was created during rendering and applies them one by one to the actual DOM elements that were in the already existing DOM tree. Now, writing to the DOM happens all in one go. So we say that the commit phase is synchronous, unlike the rendering phase, which can be paused. So committing cannot be interrupted. And this is necessary so that the DOM never shows partial results, which ensures that the UI always stays consistent. In fact, that's the whole point of dividing the entire process into the render phase and the commit phase in the first place. It's so that rendering can be paused, resumed, and discarded, and the result of all that rendering can then be flushed to the DOM in one go. Then, once the commit phase is completed, the work in progress fiber tree becomes the current tree for the next render cycle. That's because, remember, fiber trees are never discarded and never recreated from scratch. Instead, they are reused in order to save precious rendering time. And with that, we close up the commit phase. The browser will then notice that the DOM has been changed, and as a result, it will repaint the screen whenever it has some idle time. So this is where these DOM updates are finally made visible to the user in the form of an updated user interface. Now, I'm not going to go into how this phase works because this is really more about how browsers work internally and not React. However, there's still one more thing that we need to talk about. So, the browser paint phase that we just mentioned is of course performed by whatever browser the user is using. And the render phase is obviously performed by the React library. But what about the commit phase? We would think that it's also done by React, right? But actually, that's not true. It's actually a separate library that writes to the DOM, and it's called React DOM. So, not very creative, but that's just what it's called. So, in fact, React itself does never touch the DOM, and it actually has no idea where the result of the render phase will actually be committed and painted. So React only does the render phase, but not the commit phase. And the reason for that is that React itself was designed to be used independently from the platform where elements will actually be shown. And therefore, React can be used with many different so-called hosts. Now, up until this point, we have only ever thought of React in conjunction with the DOM, because we usually use it to build web application. And in 90% of the cases, that's actually what we do with React. But the truth is that React is used with other hosts as well. For example, we can actually build native mobile applications for iOS and Android using React Native. Or we can build videos with React using a package called Remotion. And we can even create all kinds of documents like Word or PDF documents, Figma designs, and many more using different so-called renderers. Now, if we think about this, renderer is actually a pretty terrible name, because according to React's own terminology, renderers do not render, but they commit the results of the render phase. But I think that this renderer name comes from a time before React divided the render and the commit phase into two separate phases. And so they chose this term of renderer because it fits with the common sense definition of rendering. But anyway, in all these situations, the result of the render phase is not really a list of DOM updates, but a list of updates of whatever elements are used in the host that's being used. So the term virtual DOM then also doesn't really make much sense when we look at it from this angle, which is just one more reason why the React team prefers the more accurate name of React Element Tree. Now, all these details are, of course, not really that important. What I want you to retain from this slide is that the React library is not the one responsible for writing to the DOM, because the DOM is just one of many hosts to which React apps can be committed, so to which they can be output, basically. And for each of these hosts, we have a different package that we can use. And that's why in our index.js file, we always import both React and React DOM, right? And so now you know the exact reason why we have to do that. All right, so after looking at all these phases in so much detail, let's do a quick recap here and summarize everything that we have learned. So, the whole process of rendering and displaying a React application on the screen starts with a trigger, which can either be the initial render of the app or a state update in one of the component instances. This then triggers the render phase, which does not produce any visual output. So this phase starts by rendering all component instances that need a re-render. And rendering in React simply means to call the component's functions. This will create one or more updated React elements which will be placed in a new virtual DOM, which is actually simply a tree of React elements. Now, what's really important to remember about this process is that rendering a component will cause all of its child components to be rendered as well, no matter if props changed or not. This is because React doesn't know whether children have been affected by the parent re-rendering or not. Now, next up, this new virtual DOM needs to be reconciled with the current fiber tree, so with the representation of the element tree before the state update. This is necessary because it would be slow and inefficient to destroy and rebuild the entire DOM tree each time that something on the screen must be updated. Instead, reconciliation tries to reuse as much of the DOM as possible by finding the smallest number of DOM updates that reflect the latest state update on the screen. Now, this reconciliation process is done using a reconciler called fiber, which works with a mutable data structure called the fiber tree. And in this tree, for each React element and DOM element, there is a fiber. And this fiber holds the actual component state, props, and a queue of work. After reconciliation, this queue of work will contain the DOM updates that are needed for that element. Now, the computation of these DOM updates is performed by a diffing algorithm, which step by step compares the elements in the new virtual DOM with the elements in the current fiber tree, so to see what has changed. So, the final result of the render phase, so basically of this reconciliation and diffing process, is a second updated fiber tree as well as a list of all necessary DOM updates. Now, it's important to note that the render phase is asynchronous, so Fiber can prioritize and split work into chunks and pause and resume some work later. And this is necessary for concurrent features and also to prevent the JavaScript engine to be blocked by complex render processes. But anyway, the output of the render phase, so the list of DOM updates, will finally actually be written to the DOM in the commit phase. So in this phase, a so-called renderer like React DOM will insert, delete, and update DOM elements so that we end up with an updated DOM that reflects the new state of the application. And unlike the render phase, the commit phase is actually synchronous. So all the DOM updates are performed in one go in order to ensure a consistent UI over time. Now, finally, once the browser realizes that the DOM has been updated, it starts a new browser paint in order to visually update the user interface on the screen. Okay, and there you have it. This is how, in a nutshell, we go from updated React elements all the way to an updated DOM and user interface on the screen. So it sure was a really long process, but I hope that you have learned a lot along the way and that it wasn't too overwhelming. And again, keep in mind that you can build React apps without being aware that most of these things even exist. Now, some of these things do have practical implications and also implications for performance, but we will talk about those later. For now, just take a breath, as this was probably the hardest part of the entire course. So, good job of sticking with it to the end, and let me know what you think of this series of lectures in the Q&A. In the lecture about the render phase, we left out one critical piece, which was the diffing algorithm that is part of the reconciliation process. So we mentioned diffing back then, but we didn't really go into how diffing works. And since that's really important, let's do that now. So diffing is, first of all, based on two fundamental assumptions. The first one is that two elements of different types will produce different trees. The second assumption is that elements with a stable key, so a key that is consistent over time, will stay the same across renders. Now, these assumptions may seem pretty obvious, especially the first assumption, but they allow the algorithm to be orders of magnitude faster, going, for example, from 1 billion operations per 1,000 processed elements to just 1,000 operations. Now, remember that diffing is comparing elements step by step between two renders based on their position in the tree. And there are basically two different situations that need to be considered. First, having two different elements at the same position in the tree between two renders. And second, having the same element at the same position in the tree. So those are the only two situations that matter. And so let's now start with the first situation. So let's say that at some point an application is re-rendered, and in the diffing process we find that an element has changed in a certain position of the tree. Now here we're actually not looking at a tree, but at the JSX code which leads to that tree, because I find that it's a bit easier to understand this way. But anyway, in the case of a DOM element changing like this, changing simply means that the type of the element has changed, like in this example from a div to a header. So in a situation like this, React will assume that the element itself plus all its children are no longer valid. Therefore, all these elements will actually be destroyed and removed from the DOM. And that also includes their state, which is really important to remember. So as we see in this example, both the div element and the search bar component will be removed from the DOM and will then be rebuilt as a header with a brand new search bar component instance as a child. So if the child elements stayed the same across renders, the tree will actually get rebuilt. But it gets rebuilt with brand new elements. And so if there were any components with state, that state will not be recovered. So this effectively resets state. And this has huge implications for the way that React applications work in practice. And that's why we will see some examples of this behavior in the next lecture. Now, everything we just learned works the exact same way for React elements. So basically for component instances, as we can see in this second example. So here the search bar component changed to a profile menu component, and therefore the search bar is again completely destroyed, including its state, and removed from the DOM. Okay, so this is the first situation. The second situation is when between two renders we have the exact same element at the same position in the tree. And this one is actually way more straightforward. So if after a render, an element at a certain position in the tree is the same as before, like in these examples right here, the element will simply be kept in the DOM. And that includes all child elements and, more importantly, the component's state. Now this may sound pretty obvious, but it actually has some important implications in practice. So, again, the same element at the same position in the tree stays the same and preserves state. And it works like this for DOM elements and for React elements as well. Now, looking at these examples, we actually see that something has changed. However, it was not the element type that has changed, but simply the class name attribute in the div and the weight prop in the search bar component. And so what React is going to do is to simply mutate the DOM element attributes, and in the case of React elements, it will pass in the new props. But that's it. So React tries to be as efficient as possible, and so the DOM elements themselves will stay the same. They are not removed from the DOM, and even more importantly, the state will not be destroyed. Now, sometimes we actually don't want this standard behavior, but instead to create a brand new component instance with new state. And so that's where the key prop comes into play, as we will learn about after seeing these rules that we just learned about in action. In this lecture, I just want to quickly demonstrate the diffing rules that we just learned in our project, so that you can see that they actually do have a practical effect in the real world. So let's start by examining a bit better what happens as we use this tab component. So again, here we have this button that when we click will hide that paragraph, right? And also when we click here, then we update the state and the likes number increases. So that's what happens in this tab. But now watch what happens when we go to another tab. So you see that the text is still hidden and the number of likes is still at 4. So what this means is that the state of this tab component instance has been preserved. Now, if we hadn't learned about this in the previous section, then this would look really strange, right? Because we would expect that whenever we go to a new tab, that the state would be reset. But that's not what happens. So as we click around here, the only thing that happens is that this title here is changed. I mean, this text down here also changes, but it stays invisible. So here the text changed, and the state again stayed the same. And the same here for the number of likes. So what is actually happening? Well, basically each time that we click on one of these tabs, the tab component down here is re-rendered. However, as we can see down here in this component tree, as we keep clicking around, we see that the tab content component instance always stays in the exact same position in the tree. And so with this, we are now in the situation that we learned in the previous lecture, where we have the same element, so in this case, the same component in the same position. And so because of that, the state is preserved across renders. So just like we learned before. So again, as we keep clicking around these tabs here, this component instance here is actually not destroyed. So it stays in the DOM, and the only thing that changes is the props that it receives. So of course, the props will change. So where is that? Right here. So you see that now as I click here, then of course, down here, the prop will have changed. But that's the only thing that changes. So the state, again, remains completely unchanged. But what if we now click on this tab number 4? So as we can see in our code, in this case, so when the tab num is 3, actually this different content component will be rendered, right? And so let's see what's going to happen. So we have number 4 here, and we have the text closed. So now we click here, and immediately we see that we get a completely different component instance right here. So it's still in the same position of the tree, but it's no longer tab content, but different content. And so now when I go back, watch what happens. So now the state has actually been reset. And so that's because the tab content that we had here before has been completely destroyed and removed from the DOM in the meantime. So while we were at the different content. And so that's why I placed this string here, which says that this is a different tab, and so it resets state. And so indeed, if we keep going here, maybe we hide this, then again, when we go here and we go back, then the state has been reset. Because again, in the meantime, this component here has disappeared, and with it, its state. So this is a direct consequence of the diffing rules that we just learned about. And so this means that these rules are very important actually in practice. So you can see the situation happening all the time. And actually we saw the exact same thing in our eat and split application. But don't worry about that for now, because we will come back to that app actually in a few lectures from now. Now, sometimes, of course, we do not want this behavior. So actually, just as I was saying in the last lecture as well. So for example, let's say I hide the details here, but then I actually expect that when I go to a new tab, that it starts again with the default. So with this opened again. So again, usually this is not what we want. And so let's take a look at how we can solve this in the next video. Remember how I mentioned the key prop when we talked about how the diffing algorithm works. And so let's now take some time to look at the key prop in detail in order to learn what it does and when we need to use it. So the key prop is a special prop that we can use to tell the diffing algorithm that a certain element is unique. And this works for both DOM elements and React elements. So in practice, this means that we can give each component instance a unique identification, which will allow React to distinguish between multiple instances of the same component type. Now that's all great, but why do we actually need this? Well, remember that the second assumption of the diffing algorithm is that whenever an element has a stable key, so a key that stays the same across renders, the element will be kept in the DOM, even if the position in the tree has changed. And this is the whole reason why we should use the key prop in lists, as we have already done so many times throughout the course. And so in the next slide, you will finally learn why we need to do that. On the other hand, when the key of a certain element changes between renders, the element will be destroyed and a new one will be created in its place, even if the element's position in the tree is exactly the same as before. And so this is great to reset state, which is the second big use case of the key prop. But let's go back to the first big use case of the key prop, which is to use keys in lists. And let's start by considering this example without keys. So here we have a list with two question items, which clearly have no key prop. But let's see what happens when we add a new item to the top of the list. Well, the two list items that we already had are clearly still the same, but they will now appear at different positions in the React element tree. They are no longer the first and second children, but now they are the second and the third children. So we basically have the same elements, but at different positions in the tree. And so according to the diffing rules that we learned earlier, these two DOM elements will be removed from the DOM and then immediately recreated at their new positions. And this is obviously bad for performance, because removing and rebuilding the same DOM element is just wasted work, right? But the thing is that React doesn't know that this is wasted work. Of course, we developers intuitively know that these two elements are actually the same as before, but React has no way of knowing that. But what if we could actually change that? Well, that's where keys come into play. Because remember, a key allows us developers to uniquely identify an element. So we can give React that information that it doesn't have on its own. And so now, when we add a new item to the top of the list, the two original elements are of course still in different positions of the tree, but they do have a stable key. So a key that stays the same across renders. So that's Q1 and Q2 in this case. And so, according to the diffing rules, these two elements will now be kept in the DOM, even though their position in the tree is different. So they will not be destroyed, and the result will be a bit more of a performant UI. Now, of course, you won't really notice this difference on small lists, but it will make a huge difference when you have a really big list with thousands of elements, which can actually happen in some applications. So, in summary, always use the key prop when you have multiple child elements of the same type. So just like the question elements in this example. And you already knew that you should do that because, well, otherwise React will complain and give us a warning. But now you hopefully understand exactly why you need to do it. All right, so we looked at the use case for a stable key, and so now let's look at the use case for a changing key, which is used to reset state in component instances. Now here we don't need a big code example because we will do this in practice in the next lecture, but let me just show you what I mean by resetting state. So let's say we have this question inside question box and we pass in this object as a prop. Now the question component instance has an answer state, which right now is set to React allows us to build apps faster. But now let's imagine that the question changes to this one. So we still have the same element at the same position in the tree. All that changed was the question prop. So what do you think will happen to the state in this case? Well, let's remember one of the diffing rules, which says that if we have the same element at the same position in the tree, the DOM element and its state will be kept. Therefore, what's gonna happen is that the state of question will be preserved, so it will still show the answer that was in the component state before. But that answer is of course completely irrelevant to this new question, right? So it doesn't make any sense to keep this state around here. So basically what we need is a way to reset this state. And as you can guess, this is where the key prop comes into play once again. So now we have a key of Q23 in this first question, which allows React to uniquely identify this component instance. Then, when a new question appears, we can give it a different key. And so, by doing this, we tell React that this should be a different component instance, and therefore that it should create a brand new DOM element. And the result of doing this is that the state will be reset, which is exactly what we need in this situation in order to make this small app work in a logical way. So, whenever you find yourself in a position where you need to reset state, just make sure that you give the element a key and that the key changes across renders. Now, this actually isn't necessary very often, but you will sometimes find yourself in this situation. And so when this happens, it's very important to know that this is the solution. Okay, and to make this even more clear now, let's go back to our small project. So let's now use what we just learned about the key prop to our advantage and fix our tabbed component. So as we have just explored previously, as we change the state here in this tab component, that state will be preserved as we re-render that component. And so again, that's because this component is exactly of the same type as before, so it stays the same element between renders, and it also stays in the exact same place in the component tree. And so therefore, its state is not reset. It is only reset when we change to a different component type here. So now that's different content, and then change back. So now in the meantime, our state was lost. But if we do this and then change here, then the state is preserved across renders. Now, as we were saying also before, this is usually not what we want. And so let's now use the key prop to change this. And actually, it is extremely easy. All we have to do is to give this tab content here a different key for each of the tabs, basically. So then each time that this tab content component here is re-rendered, it will get a different key. And so then React will see it as a unique component instance. And therefore, then the old one will be destroyed and the state will be reset. So just as we just learned in the previous lecture. And so let's do that. So let's give it a key that will change between renders. So something unique here. So let's take the content object again at the current position, and then let's, for example, take the summary. All right, so here we do not have like a unique ID, but we can see that the summary is always different. And so, as soon as the tab content component will be re-rendered, then not only this item here will change, but also the key. And so we are then in that situation where the key changes across renders. And again, that will then reset our state. So let's hide this here. Let's improve our likes, and then let's go to another tab. And beautiful. So you see that our component state has indeed been reset. And again, that's just because React now views this as a completely different instance of tab content. And we can see that here because now our DevTools display this key. And when we move here, then we get another one. And so, yeah, this is exactly how React now makes each of these tab contents here unique and distinguishes between them. Yeah, so this is really nice, really helpful. And so you really need to understand what just happened here and then keep it in mind for future situations. So I actually still remember personally when I first learned about the power of the key prop here. So this was actually a key learning moment for me. So it was really eye-opening. And so I hope I could provide the same experience here for you. So this key prop here, it looks very simple, but it can make a huge difference. And so let's now actually also use this key prop in the eat and split app that we built before. So let's do that in the next video. So, as I was just saying, let's now go back to our eat and split app to fix one problem that we have left in that application. So let's come to our desktop and then grab the project folder and open it in VS Code. Okay, and so now we have two VS Code windows open, and we will also start two React apps at the same time. So let's just write npm start, hit enter, and then it will ask you to use another port instead. And so that's simply because you're already running one app here in this other port. And of course, each one can only have one app running. So just hit enter or Y as you reached this step, and then you will see your application pop up right here. Let's get a bit more space. And then let me show you the problem that we actually left here. So let's say that we typed some values in here, and then we moved to another friend. So here we have exactly the same problem as before. So as we select another friend, the only thing that changes is really the props that is being passed here into this component. So let's check out the name of that component, as I don't remember it. So yeah, it's this form split bill. So this one receives the selected friend object. But as you see here, as we change, nothing changes in the DOM tree. And so across these re-renders, exactly the same component is rendered in exactly the same position of the tree. So just like before. And so therefore, the state is not reset across renders. But also, just like before, this is not the behavior that we would expect in this application, right? So if suddenly we move from one friend to the other one, we would certainly expect that the bill value here should be reset. So how can we do that? Well, let's see where we are using this form split bill. So that should be somewhere here in the app, probably. So yeah, here it is. And so now we basically need to make each component instance here unique, so that each time that it is rendered with a new friend, React will see this as a completely new component instance. And as you already know, the way we do that is by providing a key that will actually change across the re-renders. So here we can use the selected friend.id, I guess. So let's just see if they actually have an ID. And yeah, they have. So we could also use the name here, really. So those are also different, but the ID is really a unique identifier. So let's see. So we are at Sarah, and so therefore, let's see down here. So here we see that the key now is 933 whatever. And so let's move to another friend. And there we go. So we fixed our problem because now the component instance has another key. and so therefore it is a completely unique instance right now. Great, and that's actually it. So that's all we have to do here. So let's close this one, and let's also close this. So we are finished. We are back in our project that we were working on before. And so, yeah, there's nothing left to do. And so let's move on right to the next lecture. In order for the rendering process to work in the way that we just learned before, our render logic needs to follow some simple rules. So let's look at these rules in this lecture. But first of all, what actually is render logic? Well, in order to understand that, let's actually take a look at the two types of logic that we can write in React components. So that's render logic and event handler functions. So render logic is basically all the code that lives at the top level of your component functions and that participates in describing how the view of a certain component instance should look like. So in this code example, there is a lot of render logic. So we have these two lines of code at the top level, and then also the return block where our component returns its JSX. So these describe exactly how the component will be displayed on the screen. However, if we look closely, we can identify yet another piece of render logic here, even though this code is actually inside a function. So as you can see in the return block, the code there is actually calling this createList function. And therefore, that logic also participates in describing the component view. And so it's also render logic. So basically, render logic is all the code that is executed as soon as the component is rendered. So each time that the function is called. Now, moving on to event handler functions, those are very easy to identify. So they're basically pieces of code that are executed as a consequence of the event that the handler is listening to. So in our example, we have this line of code that essentially registered handle new answer for the change event, and therefore handle new answer is our event handler function. And this is of course nothing new at this point. So we have done this many times in the course, right? But it's still important to differentiate between these two types of logic because they do actually do fundamentally different things. So while render logic is code that renders the component, event handlers contain code that actually does things. So basically code that makes things happen in the application. So event handlers contain things like state updates, HTTP requests, reading input fields, page navigation, and many more. So all things that basically change and manipulate the application in some way. Now, why is this all so important? Well, it's important because React requires that components are pure when it comes to render logic in order for everything to work as expected. But what does pure actually mean? To answer that, let's have a quick refresher on functional programming principles, which are quite important in React in general. And let's start with side effects. So a side effect happens whenever a function depends on any data that is outside the function's scope. Or even more importantly, whenever a function modifies data that is outside its scope. And I like to think as a side effect as a function's interaction with the outside world. For example, this function is mutating an outside object, and so this is clearly a side effect. Other examples of side effects are HTTP requests, writing to the DOM, setting timers, and more. The other important functional concept is pure functions, which are basically functions without side effects. So basically, these are functions that do not change any variable outside their scope. Also, when we give a pure function the same input, it will always return the same output. For example, this function is clearly a pure function, because if we give it the same argument r, it will always give us the area of the circle based on that r value. So the output only depends on the inputs, which makes this function predictable. This other function right here, on the other hand, is completely unpredictable, because it returns a string that contains a date, and that date changes every second. So in this case, even if we give the function the same input, the output will always be different, because the date will always be different, and therefore this is an impure function. And the same is true for the second function. So notice how this function mutates an outside variable, which of course makes this function impure as well. Now, calling functions impure makes it sound as if side effects are somehow bad, but that's actually not true. So side effects are not bad in themselves. In fact, if we think about it, any program can only be useful if it has some interaction with the outside world at some point, right? Like a web application that never fetches any data or never writes to the DOM is just completely useless. However, in order to make useful and bug-free applications, we need to know when and how to create side effects, which brings us back to React and its rules for render logic. And essentially, there's just one big rule, which is that components must be pure functions when it comes to render logic. This means that if we give a certain component instance the same props, so the same input, then the component should always return the exact same output in the form of JSX. In practice, this means that render logic is not allowed to produce any side effects. So, in other words, the logic that runs at the top level and is responsible for rendering the component should have no interaction with the outside world. This means that render logic is not allowed to perform network requests, to create timers, or to directly work with the DOM API, for example, listening to events using add-event-listener. Now, according to what we learned previously, render logic must also not mutate objects or variables that are outside the scope of the component function. And this is actually the reason why we cannot mutate props, which, remember, is one of the hard rules of React. And so now you know why that rule exists. It's because doing so would be a side effect, and side effects are not allowed. Finally, we really cannot update state or refs in render logic. And updating state in render logic would actually create an infinite loop, which is why we can never do that. State updates are technically not side effects, but it's still important for them to be on this list. Now, there are other side effects that are technically not allowed as well, but that we create all the time, like using console.log or creating random numbers. So these are clearly interactions with the outside world, but they don't seem to do any harm, and so we can safely keep doing them. Alright, but now you might be wondering, if all this stuff is not allowed, then how will I ever be able to make an API call to fetch some data? Well, keep in mind that these side effects are only forbidden inside render logic. This means that you have other options for running your side effects. First of all, we saw earlier that event handler functions are not render logic, and therefore side effects are allowed and actually encouraged to be used inside these functions. And second, if we need to create a side effect as soon as the component function is first executed, we can register that side effect using a special hook called useEffect. But we will learn all about that in the next section. For now, let's move on to another super important topic, which is state update batching. So we have dived really deep into some aspects of the render phase, like the rules for render logic and how the keyprop works. But now let's take one step back and go back to one very important aspect of the first triggering phase, which is the fact that state updates are batched. So in that first lecture about how rendering works, we had this sentence, which says that renders are not triggered immediately. And so in this lecture, I want to focus on this part, which says that there is also batching of multiple setState calls. Now, as always, the easiest way of explaining difficult concepts is by using a small code example. So here we have 3 pieces of state defined using the useState hook, and we also have a button in the user interface. Then, whenever there is a click on the button, the event handler function named reset is called. In this function, the 3 pieces of state answer, best, and solved are basically reverted back to their original state. And therefore, this function is called reset. Now, actually, this is the part that interests us in this lecture. And so let's now focus only on the event handler function. Now, what I want to do here is to analyze how these 3 pieces of state are actually updated behind the scenes. So we might think that as React sees the setAnswer function call, it would update the state to the empty string as requested, and then trigger a re-render and the commit phase. Then it would move on to the next line and do the same thing again. And finally, do the entire thing one more time for the third state update. So intuitively, we would think that if there are 3 state variables being updated in this event handler, then React would re-render 3 times, right? However, this is actually not how it works. So this is not how React updates multiple pieces of state in the same event handler function. Instead, these state updates will actually get batched into just one state update for the entire event handler. So updating multiple pieces of state won't immediately cause a re-render for each update. Instead, all pieces of state inside the event handler are updated in one go. So they are batched, and only then will React trigger one single render and commit. And conceptually, it makes sense that React works this way, because if we're updating these pieces of state together, it probably means that they should just represent one new view, and therefore React only updates the screen once. So if these state updates belong together, it really wouldn't make much sense to update the screen 3 times. Doing so would also create 2 wasted renders, because we're not interested in the first 2 renders, only the final one, which already contains all the 3 state updates. Therefore, the fact that React automatically batches state updates in this way is yet another performance optimization that React gives us out of the box. Now, batching state updates is extremely useful, but it can also have surprising results. So let's turn our attention to this line of code now, where we reference the answer state variable right after updating it. So what do you think will be the value of this variable at this point? Well, let's try to think about this. So remember that component state is stored in the fiber tree during the render phase. Now at this point in the code, the render phase has not happened yet. So React is still reading the function line by line to figure out what state needs to be updated. But it hasn't actually updated the state yet, and it also hasn't re-rendered yet. That's the whole point of batching state updates in the first place, right? So what this means is that at this point of the code, the answer variable will still hold the current state, so the state before the update, even though we already told React to update it. So at this point, we say that our state is stale, meaning that the state is no longer fresh and updated. Because, in fact, a state update will only be reflected in the state variable after the re-render. And so for this reason, we say that updating state in React is asynchronous. And again, it is asynchronous because React does not give us the updated state variable immediately after the setAnswer call, but only after the re-render has happened. Now, the same thing is also true whenever there is only one piece of state being updated. So, no matter how many state variables are being updated, the updated state is only available after the re-render, not immediately. Now, sometimes we actually do need the new value immediately after updating it. And in the case that we need the new value in order to update the same state again, or in other words, if we need to update state based on a previous state update in the same event handler, we can pass a callback function into the setState function instead of a single value. And we have actually done this in practice all the time, right? Now, so far we have only talked about batching in event handler functions like our reset function. That's because before React 18, React only did automatic batching in event handlers, but not in situations that happen after a browser event has already happened. However, there are certain very important situations in which we do need to update state long after a browser event, like a click, has happened. Examples of that are timeouts and promises. For instance, we might want to run our reset function only a second after a click event, or we might want to run it after some data has been fetched. So it would be nice to also have automatic batching in those situations to improve performance, right? Well, that's actually one of the important features that React 18 gave us. So before React 18, if this reset function was called by a timeout or by a promise, state updates inside the function would not be batched. Instead, in these situations, React would actually update the state variables one by one, and therefore, in this case, render 3 times. Now, another case is handling native events using DOM methods such as addEventListener, where state updates also used to not be batched, but now they are. So again, if you're using the latest React version, you will now get automatic batching all the time, everywhere in your code. And if, for some reason, you're working with an older version of React, maybe at your work, it's important that you know that batching used to work in a different way before version 18. Now, there are also some extremely rare situations in which automatic batching can be problematic. So if you ever find yourself in a situation like that, you can just wrap the problematic state update in a React DOM.flushSync function, and React will then exclude that update from batching. But you will most likely never need this. I'm just mentioning this here so that you know that it exists. Okay, and that's it about state update batching. It turned out to be a bit longer than I thought, but as always, there's just so much interesting stuff to learn, and so I hope that you don't mind at all. But in any case, let's quickly go to the next video so I can show you some of this in practice. Alright, so let's move back to our project and see how React batches state updates in practice and how this state updating is in fact asynchronous. So let's come down here to our tab content component and then let's play around a little bit with the states that we have here. And first of all, I want to now implement the functionality of this undo button here. So this undo will basically undo or reset the 2 states that we have here. So this one and this one. So let's write a simple function, handle undo, and then what it does is set show details back to true and set the likes back to 0. And then let's use that handler right here. So easy enough, handle undo, and yeah, that works great. So as we just learned in the previous lecture, inside of this event handler function here, these two state updates are batched. So they will only cause one component re-render. Now, how can we actually prove that? Well, one simple way is to log something to the console here. So let's say render, and so then each time that the component gets re-rendered, and so then each time this console.log will log render to the console. So let's see. Let's first get rid of these other ones that we had here. So here they are. And okay. Now, never mind this one here that is a bit more grayed out. This is coming from somewhere else. So only this one render here is important. So this first render string here comes from the initial render of this tab content component. And if we go to another tab, then we get another one, because of course, then this component here is updated. Okay, now let's remove this so that we start empty. Or actually, we will see a few more. So each time that we click here, the component function gets rendered, and so then the console.log is executed. And so this is actually a really nice way of proving that rendering is calling the component function. All right, but now let's empty this. And then as I click this button here, we should only see one render here, which would then mean that these two state updates were batched. So let's see, and indeed, we only get one here. Great. Now let's also see that the state updating is asynchronous. So basically, if I try to access the number of likes here right after updating the state, then what happens? So first I need to, of course, increase a little bit. Then let's clean this. And as I reset, well, we get 5, which might be surprising, but if you paid good attention in the previous lecture, then this will actually no longer come as a surprise to you. So the reason that here we get 5 is that the state is in fact actually only updated after the re-rendering, or basically during the re-rendering, but not immediately after we call this function. So that's impossible, and therefore here we still get that old likes state, which again is still at 5. Then now it is of course at 0, because now the re-rendering has already happened. Now, by the way, what do you think will happen? So what do you think will get rendered if we click the undo button again? So let's clear this, and so let's see what happens. So I click this now, and you see that no render was logged to the console. So why do you think that is? Why was the component instance not re-rendered this time? Well, it's because both of the state values were already at their default, basically. So details was already true and likes was already 0. And so then, as we attempted to update the state, both of them were actually not updated. And again, that's because the new state was equal to the current state. And so in that situation, React will not even try to attempt to update the state, and then of course it will also not re-render the component instance. And so that's why, well, nothing happens. So as we keep clicking here, of course the console.log keeps getting executed, but again the component itself is not re-rendered. Okay, but let's move on here and let's implement this next button here. So here I have these 3 pluses, which means that when I click here, I actually want like a super like. So this should then improve by 3. So let's create a function for that, and I will just copy this one. and let's call it triple ink. And then I'll just duplicate this here. And then let's come down here on click and then handle triple ink. Okay, let's go back to our function because this will become very important. So what do you think is going to happen when I click here now? Again, let's close. So what do you think will happen to this state here in particular? So let's see. And well, it only increased once, so not 3 times as we might expect. But were we actually really expecting that it would increase 3 times? I mean, with what we already know, we should know that this here could never work. So let's see why that is. So right here at the beginning of this function, likes was 0, right? And so then here, set likes would be 0 plus 1 equals 1, right? So this one is pretty clear. But then what in the next line? So what is the value of likes here in this line? Well, it is actually still 0. And so that's because the state update is once again asynchronous. So we do not get access to the new state value after this line of code right here. And so this is exactly what happens down here. So here the state is now stale. So as we learned in the previous lecture as well. So we can very easily see that here again with this console.log. So if I click again, and actually I want the other one, so this one here, well, then you see that it became 2, which is exactly the value that we had before. And so here it was 2 plus 1 made this new 3. But here it was still 2, and here as well, and here as well. So how could we make this work if we really wanted to update the state 3 times like here? I mean, of course, we could just do this, but this is not the point here. So we are trying to learn how we could do this right here in another way. So actually, we have been doing that all along. So all the time, whenever we were updating state based on the current state, we would use a callback function instead of just a value. So we also talked about that in the previous lecture. And so now the time came where we really learn why we have been doing it with the callback function all the time. So let's remove this here or comment it out. And then let's do it the right way. So set likes, and now we pass in the callback function. And then, as you already know, the first argument here is the current value of the state, and then we just return the new one. And again, here likes could be called anything. Okay, let's do this 3 times. And then let's reload. And now, yeah, now it works. So this is the trick that changes the way the state is updated. So here in the callback function, we do actually get access to the latest updated state. So initially likes was 0, and then it returned 1. And so then in the next call here, this likes in this callback function will be 1. And so then we can update it to another one and to another one. Beautiful. And so this is the reason why I've been telling you that each time that we set state based on the previous state or based on the current state, we should always use a callback function like this here. Now, you might be wondering, like, why should we do that here? I mean, it works perfectly fine, right? And you're right about that. It works perfectly fine, but we never know what other developers might do with our functions, or even what we might do later ourselves. So let's say that at some point we want to change how this function works, and then without thinking about it, we just do this. And so then we go back to this not working as expected. So now we want to increase the likes by 2, but it will still only increase by 1, right? Or another situation, maybe Let's comment this one out. So maybe here we could think that we could just call this function here 3 times. Or maybe some other developer might think that. And so then they would get surprised when they see that this is actually not working. Right? And so, again, you should always use the callback function, because then you are always safe for whatever change your code goes through in the future. So with this, it will now work. But of course, we need to write the correct variable name. So yeah, now it does work. So even if you then use the function somewhere else, by doing this, you are safeguarded about, well, any changes that might occur in the future. All right. And now to finish, let's just prove that automatic batching now works in React 18, even outside of event handlers. So here we have this button that should undo, so it should reset our state 2 seconds later. Well, that's easy enough. Let's just create a function called handle undo later. And this function will simply set a timeout, and then after 2 seconds, it will call handle undo. So after 2000 milliseconds. And so what this will do is to schedule this handle undo function to be executed 2 seconds after this function here was called. And so then handle undo is no longer really an event handler function. It's just any function that simply gets called at a later time. So that's just what set timeout does. So let's then wire that up here with the onClick prop. So handle undo later. All right. Let's just then set our state. Let's clean up here. And then I just clicked and let's wait. And indeed, 2 seconds later, our state was updated. And indeed, our component was only rendered once, which is proved here by this single render string. Great. So again, this proves that in React 18, batching happens not only inside event handlers, but also inside a set timeout. And the same is true for promises and other situations. Now, just to really make sure, and you don't have to do this, but I like to play around with this stuff. So what I want to do now is to render this using React 17. So I will comment this one out and comment this one. Okay, and then here we need to also change here from here. And so now this is basically back to being a React 17 application. And that's exactly what it says here in this warning. So until you switch to the new API, your app will behave as if it's running React 17. But right now, that's actually exactly what we want. So now we get some error here, but yeah. So let's do some state updating here. Then I will clean and watch what happens when I click this button now. So let's wait. And now we got 2 re-renders. And so this does actually prove that before React 18, automatic batching was not happening inside a set timeout. So that's really curious. But of course, let's now put it back. All right. So this was just to show you that there really is a difference. So that React 18, well, really changed this. So again, now we should be back to only 1. Yeah, there we go. Okay, and this is actually all I had to show you here. So this was a bit longer than expected, but we did do a lot of stuff here. So after you do a quick recap of everything we just do here, or that we did here actually, then let's go to the next lecture. Let's now leave the topics of rendering and state and turn toward another essential part of React applications that we haven't really talked about yet, and that's events. So in this lecture, we will learn how React handles events and how they work behind the scenes. But let's start with a quick refresher on how event propagation and event delegation work in the DOM, because this is important to understand how React works, and also because I believe that many people don't have a good grasp on how events actually work in the browser. So let's consider this tree of DOM elements. And note that this really is a DOM tree, so not a fiber tree or a React element tree. And now let's say that some event happens, like a click on one of the three buttons. And so here is what's going to happen in the browser. As soon as the event fires, a new event object will be created, but it will not be created where the click actually happened. Instead, the object will be created at the root of the document, so at the very top of the tree. From there, the event will then travel down the entire tree during the so-called capturing phase, all the way until it reaches the target element. And the target element is simply the element on which the event was actually first triggered. So at the target, we can choose to handle the event by placing an event handler function on that element, which usually is exactly what we do. Then, immediately after the target element has been reached, the event object travels all the way back up the entire tree during the so-called bubbling phase. Now, there are two very important things to understand about this process. The first is that during the capturing and bubbling phase, the event really goes through every single child and parent element one by one. In fact, it's as if the event originated or happened in each of these DOM elements. The second important thing is that by default, event handlers listen to events not only on the target element, but also during the bubbling phase. So if we put these two things together, it means that every single event handler in a parent element will also be executed during the bubbling phase, as long as it's also listening for the same type of event. For example, if we added another click event handler to the header element, then during this whole process, both the handlers at the target and the header element would be executed when the click happens. Now, sometimes we actually don't want this behavior, and so in that case, we can prevent the event from bubbling up any further simply by calling the stop propagation method on the event object. And this works in vanilla JavaScript and also in React, but it's actually very rarely necessary, so only use this if there really is no other solution. Okay, so this is essentially how events work in the browser. Now, the fact that events bubble like this allows developers to implement a very common and very useful technique called event delegation. So, with event delegation, we can handle events for multiple elements in one central place, which is one of the parent elements. So, imagine that instead of 3 buttons, there would be like 1,000 buttons. Now, if we wanted to handle events on all of them, each button would have to have its own copy of the event handler function, which could become problematic for the app's performance and memory usage. So instead, by using event delegation, we can simply add just one handler function to the first parent element of these buttons. Then, when a click happens on one of the buttons, the event will bubble up to the options div in this example, where we can then use the event's target property in order to check whether the event originated from one of the buttons or not. And if it did, we can then handle the event in this central event handler function. Now, if you took my JavaScript course, then you will already know how to do this in practice, because, in fact, we do this all the time in vanilla JavaScript applications. However, in React apps, it's actually not so common for us to use this technique. But that might leave you wondering, if this is actually not important in React, then why are we even talking about this? Well, for two reasons. First, because sometimes you find some strange behaviors related to events in your applications, which might actually have to do with event bubbling. And so, as a good React developer, you always want to understand exactly what's going on in order to fix these problems. And the second reason is that this is actually what React does behind the scenes with our events. And so let's take a look at that. So let's consider this same DOM tree, and let's say again that we want to attach an event handler to one of the buttons or even to some other DOM element. And this is what that would look like in React code. So we would simply use the onClick prop to listen for click events and then pass it a function. So that's really easy, right? Now, if we think about how React actually registers these event handlers behind the scenes, we might believe that it would look something like this. So React might select the button and then add the event handler to that element. So that sounds pretty logical, right? However, this is actually not what React does internally. Instead, what React actually does is to register this and all other event handler functions to the root DOM container. And that root container is simply the DOM element in which the React app is displayed. So if we use the default of create React app, that's usually the div element with an ID set to root. So again, instead of selecting the button where we actually placed our event handler, we can imagine that React selects the root element and then adds all our event handlers to that element. And I say imagine because the way React does all this behind the scenes is actually a lot more complex than this, but that's not really worth diving into here. The only thing that's worth knowing is that React physically registers one event handler function per event type, and it does so at the root node of the fiber tree during the render phase. So if we have multiple onClick handlers in our code, React will actually somehow bundle them all together and just add one big onClick handler to the root node of the fiber tree. And so this is yet another important function of the fiber tree. But anyway, what this means is that behind the scenes, React actually performs event delegation for all events in our applications. So we can say that React delegates all events to the root DOM container because that's where they will actually get handled, not in the place where we thought we registered them. And so this works exactly how we just learned in the previous slide. So again, whenever a click happens on the button, a new event object is fired off, which will then travel down the DOM tree until it reaches the target element. From there, the event will bubble back up. Then, as soon as the event reaches the root container where React registered all our handlers, the event will actually finally get handled according to whatever handlers match the event and the target element. And finally, once that's all done, the event of course continues bubbling up until it disappears into nowhere. And the beauty of this is that it all happens automatically and invisibly just to make our React apps yet a little bit more performant. Now, just one small detail that I want you to notice is that it's really the DOM tree that matters here, not the component tree. So just because one component is a child of another component, that doesn't mean that the same is true in the displayed DOM tree. So just keep that in mind when thinking about bubbling in React applications. Alright, so we talked a lot about events and event objects, and so now let's finish by taking a look at how these event objects actually work behind the scenes. So, whenever we declare an event handler like this one, React gives us access to the event object that was created, just like in vanilla JavaScript. However, in React, this event object is actually different. So in vanilla JavaScript, we simply get access to the native DOM event object. For example, pointer event, mouse event, keyboard event, and many others. React, on the other hand, will give us something called a synthetic event, which is basically a thin wrapper around the DOM's native event object. And by wrapper, we simply mean that synthetic events are pretty similar to native event objects, but they just add or change some functionalities on top of them. So these synthetic events have the same interface as native event objects, and that includes the important methods stop propagation and prevent default. What's special about synthetic events though, and one of the reasons why the React team decided to implement them, is the fact that they fix some browser inconsistencies, making it so that events work in the exact same way in all browsers. The React team also decided that all of the most important synthetic events actually bubble, including the focus, blur, and change events, which usually do not bubble. The only exception here is the scroll event, which does also not bubble in React. Okay, and now to finish, I want to quickly mention some differences between how event handlers work in React and vanilla JavaScript. The first one is that in React, the prop name to attach an event handler are named using camel case, so something like onClick with an uppercase C. In HTML, on the other hand, it would be onClick all lowercase, and if we used an add event listener in vanilla JavaScript, the event would simply be called click, so without the on prefix. Now, in vanilla JavaScript, whenever we want to stop the default behavior of the browser in response to an event, we can return false from the event handler function. And the big example of that is the browser automatically reloading the page when we submit a form. However, if we would attempt to return false in a React event handler, that would simply not work. So in React, the only way to prevent the browser's default behavior is to call prevent default on the synthetic event object. And finally, in the rare event that you need to handle an event in the capturing phase rather than in the bubbling phase, you can simply attach capture to the event handler name. For example, onClick capture instead of just onClick. But most likely you will never use this, so just keep this somewhere in the back of your mind. Alright, so what we just learned in this slide is basically everything that you need to know in practice in order to successfully work with events in React. The rest all happens invisibly behind the scenes, but I hope that you also found the rest of the lecture interesting and that it gave you even more confidence in working with events in your applications. Alright, and now to finish off this section, let's talk about something entirely different. So this lecture is not really about how React works behind the scenes, but more about what React actually is, which is a library. So for future React developers like you, it's important to understand what it means that React itself is a library and not a framework. And so let's now learn about the differences as well as the React ecosystem. And to understand the difference between a framework and a library, let's start with an analogy. So imagine that you want to make your own sushi for the first time, just like I did recently for the first time as well. So you have two choices about how you want to do it. The first option is to just buy one of those all-in-one sushi kits, which will come with all the ingredients that you need. And so then you don't have to buy anything separately. All you have to do is to assemble these ingredients into your sushi. However, there is also a downside to this, because now you're stuck with the ingredients that are included in the kit that you bought. So if you find out that you don't like one of these ingredients, then you still have to use it anyway. Now, instead of getting an all-in-one kit, you also have the option to buying all the ingredients separately. And so this will give you complete freedom to choose only the best ingredients and the ones that you like the most. On the other hand, all this freedom can give you decision fatigue, because now for each ingredient you need to research which brand is the best option, and then you also have to go buy each of the products separately. And even worse, if one of your selected brands changes or is no longer sold, then you need to start the whole process over. Okay, but probably at this point you're wondering, why is he going on and on about sushi? Well, the reason is that this analogy actually translates beautifully into the difference between building a web application using a framework or using a library. So we could actually just replace the images here and call it a day. So we could describe Angular, Vue, or Svelte, for example, as the all-in-one kit, and React as buying separate ingredients. And the pros and cons of building a web app with each of these approaches are basically exactly the same as in making sushi at home. Okay, but actually let's now replace these terms with their actual definitions and actually learn what's the difference between a framework and a library. So, in the world of JavaScript, a framework is basically a complete structure that includes everything that you need in order to build a complete, large-scale application. We can say that frameworks like Angular are batteries included, because they include stuff like routing, styling, HTTP requests, form management, and more, all out of the box. Now, the downside of this is that you're stuck with the framework's tools and conventions, even if you don't like or agree with them. However, that's actually not always bad, and so this is not a real downside for some developers. Now, on the other hand, we have JavaScript libraries, which are basically pieces of code that developers share for other developers to use. And the prime example here is, of course, React, which is what we call a Vue library. Vue, because all React does is to draw components onto a user interface, so onto a so-called view. Now, if you want to build a large-scale single-page application, you will need to include many external third-party libraries for things like routing, styling, HTTP requests, and so on. So all these functionalities are not part of React itself, unlike what happens with Angular and other frameworks. And so this is how this notion that React is a library ties into the analogy of buying separate ingredients to make sushi. Because to build a React app, we have to choose all these separate libraries. Now, don't get me wrong here. We can actually build React apps with just React itself, so without using any libraries. But that only makes sense for small apps or while we are still learning React. Now, being able to choose multiple libraries in order to build your application offers you incredible freedom, because you can choose exactly the ones that you like the most. And also, every app will have different requirements, and so each app will require a different combination of libraries. And so including all of them in a framework might not even be necessary. However, on the other hand, the implication of this is that as a React developer, you need to be able to find and download all the right libraries for your specific application. And of course, on top of that, you then need to learn how to use these libraries and even stay up to date with them over time. But don't worry, it's actually not as bad as it may sound. So if you follow this course until the end, you will have a very good understanding of the most important libraries that we usually include into most React projects, which leads me actually to the next point, which is React's huge third-party library ecosystem. So React's huge popularity has led to a really large ecosystem of libraries that we can include in our React projects for different needs like routing for single-page applications, making HTTP requests, managing remote server state, managing global application state, styling, managing forms, animations and transitions, and even entire UI component libraries. Now, I will not go over all of them here one by one, because that just takes too much time, and you can also just research them if you need. So instead, I will show you which ones I consider the most important libraries, and so these are the ones that we will use later in the course. So things like React Router, React Query, Redux, styled components, or Tailwind. Now, many React developers actually do feel overwhelmed by having to take so many decisions and choosing between so many third-party libraries. And so this fact, among some other reasons, has led to the development of multiple opinionated React frameworks, such as Next.js, Remix, or Gatsby. So Next.js or Remix are React frameworks because they are actually built on top of React. So they basically extend React's functionality. And they are opinionated because other developers basically included their own opinions into how to handle stuff like routing, state management, or styling into these frameworks. So where in a traditional React app we have to make decisions about what libraries to include, in an app built with a React framework, some of these important decisions have already been taken away from you, the developer. And so this makes project development much easier and much faster, and it can also lead to a better overall developer experience. Now, different frameworks specialize in different aspects, but all of them offload much of the setup work from you. Also, all of them offer many other advantages besides just being opinionated, such as server-side rendering or static site generation. In fact, we can even describe many of these frameworks as full-stack React frameworks, because they include so many features that we can actually build full-stack apps with them, all while using React as the base layer. But anyway, this is just a brief overview of React frameworks. We will learn a lot more about this in the last part of the course, where we will actually build a very large project using Next.js. Now, this will not be included in the course at launch time, but I will include it at a later point. But at this point, I just wanted to let you know that these frameworks exist, because of course, we can only learn about them once we really master React itself and also its most important third-party libraries. Welcome to the last lecture of the section. And it was a long and complicated section, I know, but hopefully you enjoyed learning about all these internal workings of React as much as I did. And now to finish, I thought it was a great idea to summarize the key learnings that you should retain from this section. Now, this is not a summary of everything that we learned, but only the practical takeaways and conclusions that you will actually need to know in practice. So, as you build your own React apps. And this is necessary because I've mentioned multiple times that you actually don't need to know all this complicated stuff about how React works behind the scenes, but you do need to know the practical implications of it. And so in this lecture is where I gathered all those practical implications in the form of text slides that you can save and read in the future. But anyway, let's now move on to our first point, which is that a component is basically like a blueprint for a piece of UI that will eventually exist on the screen. When we then use a component, React creates a component instance, which is like an actual physical manifestation of a component which contains props, state, effects, and more. So following the analogy of the blueprint, the component is like a blueprint for a house, and the component instances are like the actual houses that have been built from that blueprint. Finally, a component instance, when rendered, will return a React element. Okay, so let's now move on to rendering. So in React, rendering only means calling component functions and calculating what DOM elements need to be inserted, deleted, or updated later. So rendering has nothing to do with actually writing, with actually updating the DOM. Writing to the DOM is actually called committing in the React language. So what I want you to remember here is that each time a component instance is rendered and re-rendered, the function is simply called again. But what actually triggers a render to happen? Well, as you should probably know already, only the initial app render and state updates can cause a render, which will happen for the entire application. So even though it might look as if only one single component is rendered, the process is actually executed for all components. Now, when a component instance does get re-rendered, all its children will get re-rendered as well. Now, this doesn't mean that all children will get updated in the DOM, because thanks to reconciliation, React will check which elements have actually changed between the two renders. Now, one of the main parts of this reconciliation that I just mentioned is diffing. So, diffing is how React decides which DOM elements need to be added or modified later. Now, if between two renders a certain React element stays at the same position in the element tree, the corresponding DOM element and the component state will simply stay the same. So the DOM will not be modified in this case, which is a huge win for performance. However, if the element did change to a different position in the tree, or if it changed to a different element type altogether, then the DOM element and the corresponding state will be destroyed. So they will basically be reset. Now, one cool thing about the diffing algorithm is the fact that we can actually influence it by giving elements a key prop, which then allows React to distinguish between multiple component instances of the same component type. So when the key on a certain element stays the same across renders, the element is kept in the DOM even if it appears at a different position in the tree. And so this is the reason why we need to use keys in lists, because it will prevent unnecessary recreations of elements in the DOM. Now, on the other hand, when we change the key between renders, the DOM element will be destroyed and rebuilt. And so this is a very nice trick that we can use in order to reset state, which is sometimes necessary, as we saw in two practical examples in this section. Next, we have one very important rule that you must never ever forget, which is that you should never declare a new component inside another component. That's because doing so will recreate that nested component every time the parent component re-renders. So that nested component would always be a new variable, basically. And so this means that React would always see the nested component as a brand new component, and therefore reset its state each time that the parent state is updated. Now, the reason why this happens is not the important part, but what matters is that you should always declare, so you should write new components at the top level of a file, never inside another component. Now, the logic that is responsible for creating DOM elements, so basically logic that produces JSX, is called render logic. And this render logic is not allowed to produce any side effects. So render logic can have no API calls, no timers, no object or variable mutations, and no state updates. The only place where side effects are allowed is inside event handlers and inside useEffect. Okay, now after all this rendering, it's time to finally update the DOM, which happens in the commit phase. However, it's actually not React that does this committing, but a so-called renderer called React DOM. That's why we always need to include both these libraries in a React web application project. We can also use other renderers to use React on different platforms, for example, to build mobile or native applications with React Native. Alright, and now for the rest of this last slide, let's leave the topics related to rendering behind and quickly talk about state and events. So, when we have multiple state updates inside an event handler function, all these state updates will be batched. So basically, they will happen all at once. And this is super important because it means that multiple related state updates will only create one re-render, which once again is great for performance. And since React 18, automatic batching even happens inside timeouts, promises, and native event handlers. Now, one super important practical implication of this is that we cannot access a state variable immediately after we update it, which is why we say that state updates are asynchronous. Next up, when we use events inside event handler functions, we get access to a so-called synthetic event object, not the browser's native object. So the React team created synthetic events so that events work the exact same way across all browsers. And the main difference between synthetic and native events is that most synthetic events do actually bubble, and that includes the focus, blur, and change events, which do usually not bubble as native browser events. The only exception here is the scroll event. Okay, and now finally, let's remember that React is a library and not a framework. This means that you can basically assemble your applications using your favorite or the community's favorite third-party libraries. And this is great for flexibility and creative freedom. The downside of this freedom is that there is an basically infinite amount of libraries that you can choose from. And so you need to first find and then learn all these additional libraries that you need. However, that's not that big of a problem because you will learn about the most commonly used libraries in the main projects of this course. Alright, and there you have it. So this is essentially what I need you to remember from this section going forward. And again, I hope that you found this section as interesting as I did. But no matter if you did or not, please leave your comments about it in the Q&A section. And now, maybe take some time to basically recover from all this new material and all these new concepts that you learned. And then, once you're done, I see you in the next section.